First of all, I would like to say thank you to Giuseppe for the invitation. I'm very grateful to discuss about the experimental methods for the mechanical characterization of industrial components produced by additive manufacturing with all of you. Before starting, I want to present the scenario in which this research activity is inserted. Thanks to the funds made available by the European Community, additive manufacturing has become a real link, a link between the industries and the university, and also the research institutions. This new technology, in fact, needed a strong experimental and theoretical support, which consequently produced many and many literature works. I, obviously together with the construction of machine team, we are working in support of these issues to answer to this additive manufacturing problem in collaboration with the NTNU of Trondheim and with some companies such as Apcapi Coxa or Synergy Approaches or also Aeronautica Militare. Basically, the real question that the industrial world wanted to answer is really possible to replace structural components? Or better, in other words, at the mechanical resistance level, is it possible to replace a classical manufacturing process with an additive one? But this need is mainly due to the fact that there is a lack of a clear and consolidated characterization of the mechanical properties of the final components. These final components are the result of various phases, very closely and very linked together. We start from the choice of process parameter that historically is the first research activity were carried out in this area. Today, the providers of additive manufacturing machines, but also the providers, for example, of the powders, already produce and optimize the parameter set that sometimes give to the industries that booked the machines. So it's difficult and is require also a considerable experience that in the most of the case the industry doesn't have to be able to create a new optimal set of parameters. The process parameters directly influence the microstructures, but in the end we can ask to ourselves, what are the mechanical properties of these components? With mechanical properties, I mean all of those fundamental properties for the design phase of any structural components. So basically the static resistance, the elasticity, so the Young modulus, and the fatigue limit, or better also the slope of the Wheeler curve. But the goal is to provide to the industry with a valid support for the mechanical characterization of the components made by additive manufacturing. We must go to plan the mechanical characterization tests. First of all, we must also to define if we want to investigate the dependence of mechanical properties on some variables. And then define the investigation plan. so planning and carried out the tests. If we go in details of this first step, so the definition of these variables, we can evaluate, for example, the mechanical characterization, varying the powders or varying some process parameters such as the speed or the power or some other parameter. Other variables could be, for example, the grow directions, and this is a parameter that is very important that is linked to the geometry of the spaceman. Another is possible to investigate if the component is machined or not, so we can evaluate the as-built state or the machined state. Another could be the evaluation of the head-treated spaceman. So at the end, also in accordance with the standard ISTM, we can define a table in which all the variability and the adequate number of spacemen are contemplated. For a correct experimentation is necessary to start from the definition of the as-built state. Also, if the as-built state is not very used in the industry world, for example, the titanium, we know that have the obviously an accessory of head treatment. But we need the as-built characterization, mechanical characterization, to start also for to compare the as-built characterization with the other characterization, with the other varying the other parameter. Once we have finished to planning the test, we can start with the mechanical characterization, the real mechanical characterization, and we start with the static mechanical properties. In most cases, and I want another time stress that I talking about an industrial level. So inside an industry, this is not carried out because if you see the material data sheet of the most relevant machine manufacturers, the static characterization is almost always defined, and if we go in detail, for example, for the SLM solutions, we can see inside this simple datasheet that for a particular set of parameters, we can see that the mechanical, statical, mechanical properties are defined. Are defined also for an as-built, but also for an threaded and for 3 builds of directions. So what the industries usually want to do is characterize their additive manufacturing for fatigue strength. For example, this is a research activity carried out by our group and in collaboration with the NTNU of Trondheim on TI-64 spacemans that are standard titanium powders. The tests are conducted for Synergy Process company and are produced in 2 building directions and after tested in their as-built state. As-built, so no head treatment, the detachment from the platform was done use a controlled precision blade, and supports also are cleaning manually, and the tests are done with a load frequency of 20 Hz, load ratio R equal to 0.1, and we take a run out when we have 2 million cycles. Also, more detail, you can see the paper that we produced consequently of this research activity. 9 specimens were tested for each direction of growth, and the Wheeler curves were plotted by performing 2 run-out for each set. As we can see from the figure, the curve of the vertical spacement is constantly kept below the curve produced by the horizontal spacement. The fatigue limit is obviously lower than the classical one that we can find in literature for the TI-64 produced using classical technology. But let's go through evaluate in detail what the causes could be. First of all, the analysis of the surface roughness. We very well know that the surface roughness is one of the most parameters that influence the fatigue strength. So the surface roughness on the lateral face of the spacements is the same for the vertical and for the horizontal one, and is equal to 29 micrometers. The oxidation and adhesion of unfused particles represent one of the factors that determine this quality, this value of roughness. If the surface roughness remains constant for all the faces for the vertical spacement, this is not true for the horizontal spacement, because where we cut the supports, the roughness the value of the roughness is more elevated. But we can go in more detail. We can analyze the fracture surface of the vertical spacements, also for the horizontal spacements. If we compare this analysis, we can see that in all the 7 cases analyzed for the vertical spacements, so for all the spacements broken, the propagation of the fracture starts from a single point, where the surface have a defect, but the ignition does not have a preferential side, so the crack starts can start from all the surface of the spacement. In the other hand, the horizontal spacements in all the 7 cases analyzed have an ignition location that have a preferential location. So the propagation of the fracture begins in each case from the side where the support were removed. In both cases, the vertical and horizontal, no internal defects are involved in the propagation of the fracture. The maximum dips of the surface defects obtained from the fractography is 122 millimeters for the vertical spacement and 324 millimeters for the horizontal spacement. Another factor that we have to analyze for his important influence on the fatigue strength is the residual stress. At the end of the fabrication of the spacements, a residual stress offshore was induced. This is due to the high temperatures correlated with a rapid cooling process, characteristic of the additive manufacturing process. Starting from high temperature peaks, for example, in a classic SLM process involving titanium powders, maximum peaks are 2436 degrees. And after that, we have a very fast cooling. The rate is in the range of about 10 power 4, power 6, so a very high, very fast cooling. And at the end, layer by layer is generating a force capable to create a detachment from the platform, which is more evident in horizontal spacements. In this case, in fact, we can see the classical banana deformation. It is very difficult to analyze the residual stress to predict it. And ANSYS Additive Suite is one of the most powerful simulation tool, and with this we are capable to predict the residual stress, or better, to evaluate also a qualitative and comparative evaluation in terms of normalized vertical displacement, for example. It's possible to see from the figure that we have a very marked opposition between the peripheral areas and the central area of the spacement. In other words, we have a positive displacement on the peripheral area, and we can arrive also to a negative displacement in the central of the spacement. This is create an opposition, so we can analyze also with another slide also in a qualitative way what is the stress induced inside the spacement. Obviously, this situation, but in very low displacement, very low opposition of displacement, occurs also in the vertical spacement. As anticipated, we are also going to investigate in more detail the set of stress generated by this deformation inside the horizontal spacements. And this deformation creates a particular distribution of stress that is like a bending inside the samples. And this bending obviously have an influence on the fatigue strength. Then we arrive at the conclusion. So when you want to produce some structural additive manufacturing components, you must know the mechanical, static, and dynamic characterization of the material used. And for this reason, we have illustrated a simple process flow that a company can use to acquire the basic mechanical properties of their components produced by additive manufacturing technique, and that they can be used at the industrial level. So we stress again that we we have seen only the analysis of an as-built spacements, but we can also use this same flow, analysis flow, to analyze also subsequent, for example, add treatment or some machine treatment, and so on. I want to say thanks again for the invitation. Thank you for listening, and leave my contacts not only for any question but also to propose future activity or to propose possible lines of common research activity. And I believe that the aim of this workshop is also this, so don't hesitate to contact me. Thank you.